Tempering is a process of heat treating, which is used to increase the toughness of iron-based alloys. Tempering is usually performed after hardening, to reduce some of the excess hardness, and is done by heating the metal to some temperature below the critical point for a certain period of time, then allowing it to cool in still air. The exact temperature determines the amount of hardness removed, and depends on both the specific composition of the alloy and on the desired properties in the finished product. For instance, very hard tools are often tempered at low temperatures, while springs are tempered to much higher temperatures. Introduction. Tempering is a heat treatment technique applied to ferrous alloys, such as steel or cast iron, to achieve greater toughness by decreasing the hardness of the alloy. The reduction in hardness is usually accompanied by an increase in ductility, thereby decreasing the brittleness of the metal. Tempering is usually performed after quenching, which is rapid cooling of the metal to put it in its hardest state. Tempering is accomplished by controlled heating of the quenched workpiece to a temperature below its lower critical temperature. This is also called the lower transformation temperature or lower arrest temperature, the temperature at which the crystalline phases of the alloy, called ferrite and cementite, begin combining to form a single-phase solid solution referred to as austenite. Heating above this temperature is avoided, so as not to destroy the very hard, quenched microstructure, called martensite. Precise control of time and temperature during the tempering process is crucial to achieve the desired balance of physical properties. Low tempering temperatures may only relieve the internal stresses, decreasing brittleness while maintaining a majority of the hardness. Higher tempering temperatures tend to produce a greater reduction in the hardness, sacrificing some yield strength and tensile strength for an increase in elasticity and plasticity. However, in some low-alloy steels, containing other elements like chromium and molybdenum, tempering at low temperatures may produce an increase in hardness, while at higher temperatures the hardness will decrease. Many steels with high concentrations of these alloying elements behave like precipitation hardening alloys, which produces the opposite effects under the conditions found in quenching and tempering, and are referred to as maraging steels. In carbon steels, tempering alters the size and distribution of carbides in the martensite, forming a microstructure called tempered martensite. Tempering is also performed on normalized steels and cast irons, to increase ductility, machinability, and impact strength. Steel is usually tempered evenly, cooled through tempering, producing a nearly uniform hardness, but it is sometimes heated unevenly, referred to as differential tempering, producing a variation in hardness. History. Tempering is an ancient heat-treating technique. The oldest known example of tempered martensite is a pickaxe which was found in Galilee, dating from around 1200 to 1100 BC. The process was used throughout the ancient world, from Asia to Europe and Africa. Many different methods and cooling baths for quenching have been attempted during ancient times, from quenching in urine, blood, or metals like mercury or lead, but the process of tempering has remained relatively unchanged over the ages. Tempering was often confused with quenching and, often, the term was used to describe both techniques. In 1889, Sir William Chandler Roberts Austin wrote, "There is still so much confusion between the words temper, tempering, and hardening, in the writings of even eminent authorities, that it is well to keep to these old definitions carefully in mind. I shall employ the word tempering in the same sense as softening terminology. In metallurgy, one may encounter many terms that have very specific meanings within the field, but may seem rather vague when viewed from outside. Terms such as hardness, impact resistance, toughness, and strength can carry many different connotations. making it sometimes difficult to discern the specific meaning. Some of the terms encountered, and their specific definitions are: strength. This is resistance to permanent deformation and breaking. Strength, in metallurgy, is still a rather vague term, so is usually divided into yield strength, tensile strength, and shear strength. Toughness, resistance to fracture, as measured by the Sharpe test. Toughness often increases as strength decreases. Hardness. Hardness is often used to describe strength or rigidity, but, in metallurgy, the term is usually used to describe resistance to scratching or abrasion. In conventional metal alloys, there is a linear relation between indentation hardness and tensile strength, which eases the measurement of the latter. Brittleness. Brittleness describes a material's tendency to break before bending or deforming either elastically or plastically. Brittleness increases with decreased toughness, but is greatly affected by internal stresses as well. Plasticity. The ability to mold, bend or deform in a manner that does not spontaneously return to its original shape. This is proportional to the ductility or malleability of the substance. Elasticity, also called flexibility, this is the ability to deform, bend, compress, or stretch and return to the original shape once the external stress is removed. Elasticity is inversely related to the Young's modulus of the material. Impact resistance. Usually synonymous with high-strength toughness, it is the ability to resist shock loading with minimal deformation. Where resistance. Usually synonymous with hardness, this is resistance to erosion, ablation, spalling, or galling. Structural integrity. The ability to withstand a maximum rated load while resisting fracture, resisting fatigue, and producing a minimal amount of flexing or deflection, to provide a maximum service life.